In regression, when is the maximum likelihood estimate equivalent to the least squares estimate? So let's start off with an overview of the maximum likelihood estimate and then compare it against the least squares estimation method. In maximum likelihood estimation method, our aim is to find the values of parameters that will maximize the likelihood of observing the given data set. Let's take the example of normal distribution, whose density is given by this function. Let's say this is f of x, and we have the parameters theta, which is mu and sigma. What we are interested in is what's the probability of observing the given data given some value of parameter theta, which we write as f of x1, x2 up till xn given theta. And since x1, x2 are independent, we write it as f of x1 given theta times f of x2 given theta. And the value of theta that will maximize this product of probabilities, that is our maximum likelihood estimate of theta. Now to find the maximum, we differentiate it with respect to our parameters theta and equate it to 0. But to make it easier, we first take the natural log of the function and then differentiate it with respect to each of our two parameters, that is mu and sigma. So first we take the log, then differentiate it with respect to mu once, and then differentiate it with respect to sigma once and equate it to 0. We put in the value of f of x, which is normal density. We take a natural log. This splits the multiplication into the summation terms. Then we differentiate it with respect to mu. So the first term becomes 0 as it's independent of mu. We are left with this second term here. We differentiate it with respect to mu to get this term here. Now the key to answering this question is to note the occurrence of x minus mu in the normal density. And as we'll see, this will relate to the sum of squares in the least squares estimation method. So we get the maximum likelihood estimate of the mean mu equal to sum of xi's divided by n, and similarly we differentiate with respect to sigma to get the maximum likelihood estimate of sigma as the square root of mean of square deviations from the mean mu. Now coming to the least squares method, we have the model y is equal to x beta plus e, and sum of squares is given by E transpose E, which from this model we can write it as y minus x b. Our goal here is to minimize sum of squared errors, which is E transpose E. We can write it as y minus xb transpose times y minus xb. We open the brackets and differentiate it with respect to b and equate it to 0. This gives us an estimate of b. Our main concern here is with this objective function which we are minimizing, which is y minus xb transpose times y minus xb. To visualize this, consider a simple linear model. We have y on this axis, x on this axis, and the conditional distribution of y for any given x we know is normal with mean as mu. Mu in this case of simple linear model is x beta. Now our aim in least squares is to minimize the sum of squared errors, which in this case is this difference. Now this difference also occurs in maximum likelihood function as x minus mu squared, and minimizing this difference maximizes the maximum likelihood function, as we'll just see in the next slide. So this is the log likelihood function of a normal distribution, and this is the term which we were just looking at. So maximizing the log likelihood function would require that we minimize the value of this term, and as we have just seen, this term is the same as the other term which we minimize in the least squares estimation method. So the least squares estimation method, which requires minimizing the sum of squared errors, would correspond with the maximum likelihood estimate method because of the term x minus mu squared, which occurs in the normal density. So to summarize the answer, the maximum likelihood estimate and the least squares estimate would be equivalent when the distribution is normal. And that's because when we are optimizing the mean to minimize the sum of squares, that's the same as maximizing the log likelihood when the distribution is normal. And as we have seen, this happens because of the term x minus mu squared inside the exponential structure of a normal PDF, which other distributions do not have. And that's the answer to this question.